Happy New Year, everyone, and welcome to Lifelong Learning. We're having a little technical difficulty, so bear with us. Please be sure to silence your phones before we start. And this is our first presentation of the new year, and in a few days, a recording of this presentation will be available in our members-only video library on our website. Our members enjoy many benefits of being a club member, and the best benefit for me, anyway, is our very talented video team recording every presentation, which is then posted on our website. But you need to be a member to access it. Before I tell you about our exciting programs coming up, the Association would like you to know that the views expressed in our presentations are those of the presenter and may not reflect the views of the Association or our club leadership.
Happy New Year, everybody. It's nice to see so many people who made it out this morning. And I'm looking forward to this presentation. Climate change is on everybody's mind, and I'm so glad that we have a fellow who's done years and years of research on it. So this first part is going to be about a history of information about Earth's energy obtained from astronomical data from outside our planet. Next week, we're going to talk about data collected on the planet and how it relates to climate change. So without further ado, please let me introduce John Waterhouse, who has a master's degree in physics and a bachelor's of science in math. Mr. Waterhouse.
So with that, what we're going to do today, we're going to talk about climate change, and I can assure you this is going to be from a total different perspective from what you probably are used to. A totally different approach. Not that there's anything wrong with the other approaches. There are many, many factors that affect climate and potentially our ability to alter the natural flow of climate change. So we're going to take a look at two of these, two different perspectives. Now let me see here, I'm pushing the button, and I have a habit of pushing the wrong button when I do this. Okay, so far the first step actually worked out. So today what we're going to do, two different things that usually are not done. First thing is we're going to go beyond Earth into outer space and see if there is anything out there that might be of curious in dealing with climate change. And then the second part of this is we're going to go back into the geologic history of the Earth and see what we might be able to find from there. Now, you know and I know that it's common to look at temperature changes over 10, 20, 30 years, but we're going to go way back. In fact, in some cases, we're going to go back to the origination of the Earth and see what we might be able to pick up from this. So what we're going to do, in other words, we're going to learn from what can we learn from astronomy and what can we learn from geology. Okay, we're going to start off with the astronomy part. And the first thing we're going to do is we're going to visit the sun. And you might ask, why in the world are we going to talk about the sun? What does that have to do with climate change? And my response would be plenty. And the reason being is because all weather systems, which ultimately determine climate, are heavily driven by energy. Even a simple little rainstorm, just a very calm pouring of rain for just a few minutes, and then the clouds disappear, that involves a tremendous amount of energy transformations. And as the weather activities get stronger into hurricanes and tornadoes, et cetera, the problems, the energy transfer becomes much, much larger. And the sun is our predominant source of energy on Earth. Just about everything comes from the sun. There is a secondary source of energy which is totally independent of the sun, and it plays a very, very important role in our climate, in our planetary system, and we'll talk about that also in this presentation. Now, what we're going to do is, I'm going to tell you some things that are happening with the sun. You may be familiar with this, you may not be familiar with it. But the information that I'm going to show you on the screen has been known for years by astronomers, by scientists, but it's not really well discussed. This may come as a surprise. Some of you will be familiar with this, some of you will not be. But the information that you're going to see has been known for years, probably several hundred years. And we're going to come back. I'm going to start with the conclusions. I'm going to tell you where this ends up. And then we're going to take a look at where this information comes from. Okay, well, the news is not very good. The sun is getting larger with the passing of time. The surface of the sun is getting hotter with the passage of time. At some point, the sun will engulf our nearby planets, Mercury and Venus. That's right. The sun will become so large that it will swallow up those planets. It may or may not engulf Earth. Well before Earth is engulfed, all forms of life on Earth will become extinct. Aren't I bringing you great news? Now, the good news is this is going to take many, many years for this full system to develop. In fact, it might be so far out in the future that you might say, why are we even discussing it today? I mean, this is absolutely ridiculous. However, you're going to see as we progress through this presentation, you're going to see that the changes are occurring gradually, and the changes are already occurring right now. The sun has already killed all the planets near Earth, Mars, Venus, and Mercury. That is what the scientists believe. They believe that that's been the situation. Now, they killed our nearby planets. All three planets were believed by scientists to have been at one time exactly like Earth. The reason being is because these four planets, Mars, Venus, and Mercury, occupy the same general region in our solar system, with the other planets much further out, much further away from the sun. And we know today that the hard, solid portion of these planets are very, very identical. And it is believed that in the past, that all four of these planets probably looked exactly the same way. There's no signs of life on our neighbors, either today or in the past. However, scientists firmly believe that at some point they probably will find some evidence of life having had existed in the past, just because the planets are so identical. There's no signs of any surface water on the other three planets. However, all the planets have what appear to be dried up riverbeds and dried up lake beds, indicating that at some time they had water. Okay, where does all this information come from? How do we know that the Earth is eventually on its deathbed? Okay, so we're going to take a look at where this information originally came from. First of all, humans have been on the Earth for around 200 to 300,000 years. If you want to become more primitive, you can even go back further, although this is far enough. Humans have always been very interested and amazed by outer space. From the day that they walked on this planet, they cannot help but wonder, what in the world on a clear, cloud-free night, what in the world are these little white shiny dots up in the sky? So it's very possible that if astronomy was not the very first science that man developed, it certainly would be among the earlier developing sciences. The fundamental telescope dated all the way back to the time of Galileo, and this brings you back to in the early 1600s, and he made significant contributions to the field of astronomy, not only with reference to our solar system, but also the deep outer space. So over the years, humans have developed a detailed understanding of how stars behave, what they do, their life cycles, et cetera, et cetera. We still have an awful lot to learn about how they work, and the particulars, but they certainly have understood exactly what we can expect from these stars, these little white dots in the sky. Stars come and go. They are constantly, new stars are being developed, being formed, and old stars run out of energy and just disappear from the sky. In fact, let's take a couple of seconds and talk about exactly what a star is, as best as we know it today. A star is basically a natural fusion nuclear reactor, producing tremendous amounts of energy. And the energy is radiated out in the form of electromagnetic radiation, and for each star sends the radiation out billions and billions of miles. It is just a tremendously powerful source of energy. And there are plenty of stars in the sky. Scientists believe there are billions of stars. Not only that, but stars are grouped together in groupings called galaxies. We live in the Milky Way galaxy. And scientists today believe that the universe consists of billions of galaxies, and each galaxy containing billions of stars. So we've had plenty of little white dots for humans to be studying over the years. Now, all stars have a life cycle. During their age of existence, they go through different phases. Different stars have slightly different life cycles. However, all stars have a period in their development where the star is growing in size, it's becoming larger, and the surface temperature is increasing, which is where the sun's life cycle is right now. Now, this means the energy hitting the surface of the Earth is constantly increasing. Now, this is a screen capture off of the NASA website, National Aeronautics and Space Administration. Like all stars, our sun will eventually become so large that it will engulf Mercury and Venus and possibly Earth. So that's right on the website. As I say, this has been known for years. If you're not familiar with this, it's either because you don't follow astronomy, and maybe you follow astronomy, but you just haven't followed this particular aspect of astronomy. Here is a diagram of the life cycle of the sun. And you can see the sun is expected to last 14 billion years in total, the timeline on the bottom. You can see they last a little longer than we humans. It's believed by scientists that the sun is roughly 4.5 billion years old. And the pictures tell you two pieces of information. The size of the circles show you that the size of the sun is increasing. And the color of the halos and also inside of the circle gives you an indication of the temperature. And you can see up there the warming phase. The sun is in its warming phase. And then all of a sudden at some point, at roughly 10 billion years out, the sun tremendously goes through a very rapid expansion. At what point this is called a red giant. There's a number of interesting theories on what causes that, and we can discuss that if anybody has any questions during the open discussion after the presentation. But at that point, the sun becomes tremendously large, and the temperature grows tremendously also. By the way, this diagram and the next two diagrams are not to scale at all, not to scale. This diagram infers that, maybe the red giant is twice as big as the sun before. The red giant is many, many times larger. It really increases in size tremendously. Then after it's a red giant, it begins losing its fuel, and At that point, it drops down to what's referred to as a white dwarf. It's on its deathbed at this point, but because of the immense size of stars, it's going to take estimated 3 billion years for the thing to die out completely. And then when it dies out, for the most part, what happens is it disappears from the sky. That's the end of it. And for the most part, that's the end altogether. Now, just as a point of interest, which really doesn't have anything to do with global warming, something really interesting happens when extremely large stars disappear. When they die, a very weird phenomena occurs. The star disappears from the sky, and then all of a sudden, the stars right in the near vicinity of the disappearing star, all of a sudden their motion trajectory changes tremendously, and those stars start orbiting around the space where the previous star had just disappeared, which is an amazing phenomenon. And that phenomena is referred to as a black hole, the formation of a black hole. I'm sure you've probably heard of a black hole from one time or other. We don't know much about that. We do know that what it causes. And what happens is that star is replaced with a tremendous amount of gravitational force, of gravity, and that is a real mystery on exactly what happens and why it happens. But anyway, it doesn't have anything to do with global warming. Imagine waking up in the morning and seeing a sunrise that looks like this. I'm not sure why this is giving this a different picture here. Didn't happen on my computer, but this is showing some of the slides a little bit differently. But take a look at that sunrise. Imagine waking up seeing a sunrise that big. This is a simulation of what might happen if you were on the surface of the Earth when the star became a red giant. And you can see that that sun is so large, it is butting right up against the planet Earth. And if you look down at the ground below, it certainly looks different than ground looks like today, because long before this would occur, all water on the surface of the Earth would have evaporated, and all life on Earth will become extinct. Now, this is, we're going to kind of change course for just a couple of minutes here. We're going to consider the question, how much energy do all humans use in their lifestyles all throughout the entire Earth? And how does that compare with the total amount of energy that comes from the sun and actually strikes the surface of the Earth, the hard surface of the Earth, the ground? How much energy do we use that comes from the sun? There's a lot of information on the internet about this, but most of the postings are going to involve a considerable amount of calculations to actually come up with that ratio. Well, this has done very, very nicely by the University of Alberta in their posting. And the University of Alberta is well positioned to make such of a posting because they have a large research division which is researching future power generation and energy systems of the future that will power the needs of humans in the future. So there's more than enough solar power to meet our energy needs. Now, the next slide is going to take that line in purple and blow it up so you can read it for yourself. This is absolutely amazing if you stop and think about it. In less than 8 hours, enough sunlight hits Earth to meet all of humanity's needs for a full year. In 8 minutes, it's enough for a full year. There is a tremendous capability for solar power systems. The only problem with them today is that they are so inefficient. And there's a lot of research going on, and I'm sure that at some point there will be scientific breakthroughs in that. So there is good hope for this thing. Now, this was published, this was developed, this ratio came from information that was accumulated by the International Energy Agency during the year of 2014, and they put this ratio together. Now, 8 hours divided by 365 days, that is a ratio of less than 1/10 of 1%. All of humans needs, everything that we do, less than 1/10 of 1%. Granted, we share the planet with many different species of life, but it's hard to believe that any of those species use anywhere near as much energy as we do. We have a lot of ingenuity. We've developed means of transportation. We've got cars, boats, planes, trains flying all over the atmosphere. We got manufacturing plants and utility systems and everything else. No species on Earth ever does anything a lot like that. And of course, all species need some form of energy from the sun in order to survive, but probably very, very little compared to the consumption done by humans. This is another posting from the NASA website. Over the course of the next 20 million years, yes, this is a far out in the future, the sun's luminosity will increase to 5,000 times what it is today. 5,000 times. Luminosity is a measure of light brightness. It's measured in a unit called lumens. But whatever the luminosity increase is, that's just the entire increase in energy. The entire electromagnetic spectrum, including your infrared areas, your ultraviolet, and everything, it all increases 5,000 times its current radius, its current level. And the radius of the sun grows to 1 AU. Now, AU stands for astronomical unit. 1 astronomical unit is 93 million miles. 1 astronomical unit is the distance of the centers, the distance of separation of the centers of the sun and the earth. So if the sun has an exact radius of 1 AU, what that means that the sun will engulf half of the earth, with the would-be surface, if you will, of the sun slicing right through the center of the earth. Now, we don't know if it's going to be 1 AU or a little bit more or a little bit less. That's the reason why they say that it may or may not engulf Earth. It will engulf Mercury and Venus because they are closer to the sun. And they have the 1 AU would easily engulf them. Okay. I think we got everything here. So, conclusion so far, with ever-increasing energy being radiated to the Earth from the sun, which is already receiving energy well in excess of what is needed, the goal of decreasing surface temperature of the Earth will be presented with headwinds. I think that's obvious. How much headwinds? And how does that compare with our attempts to mitigate climate change and to try to reverse the increasing temperature? We don't know. We don't have an answer to that. It could be our mitigation attempts tremendously overpower these headwinds. Then again, it could be the other direction too. We just don't know. So a question to consider, with the sun currently over-energizing the Earth and that energy constantly increasing, can we realistically expect human efforts to cool the planet to be successful? I don't think this has an answer. In fact, it certainly doesn't have an answer. We just have to wait and see what happens. We've got many mitigation processes in operation, and we also have some significant problems with the sun pushing this process in the opposite direction we want to see it. Okay, now at this point we're done with the sun. So just to conclude the situation here, sun is getting bigger, it's getting brighter, it's constantly giving us more and more energy. Now today we're going to look at our solar system with the emphasis on Mercury, Mars, and Venus. For two reasons. Well, basically, scientists believe by looking at these planets gives us a pretty good idea of what's going to happen to Earth in the future. And again, these planets occupy the same general region of the solar system, Their hard design, the ground design, the physical material of the solid part of the planets are exactly identical. They were comprised of the same solar stuff floating around when the planets were formed. Okay, let's see here. Here's a diagram of our solar system, and these diagrams are not to scale, but basically the big components of our solar system involves the sun at the center and 8 or 9 planets, depending upon whether you want to consider Pluto a planet or not. Some scientists do, some don't. This one shows 8 planets, all orbiting around the sun, just like Earth. They all go around the sun, and they all have tilted axis of rotation. They all rotate just like we do day and night, and they all have seasons. They have part of the planets receive heat during what would be a summer season and a winter season. So they all pretty much operate the same way, even though the planets are significantly different, especially the outer ones. Now this diagram shows how nicely neat all of these orbital patterns are. Just the adjacent patterns are just nicely equal distant from each other. They absolutely are not. As you move away from the sun, the distance of adjacent orbits tremendously increases. And those outer planets, Saturn, Jupiter, are really, in fact, some scientists say it's almost difficult to even consider them part of our solar system. Here's a little bit of a diagram that's a little bit different. It shows you the order in terms of the proximity to the sun, and it gives you a rough indication of size ratios. But this diagram, if you look at it, shows the Earth is, Jupiter is about maybe 15–20% larger than Earth. Jupiter in reality is over 100 times the size of Earth. So these diagrams are not to scale. This is the best diagram at all. It kind of categorizes our planets. And you can see Earth, Mercury, Venus, and Mars are right together. They are referred to as the rocky planets. And again, all of the hard surface, the solid surface of the planets are very, very much identical. They occupy the same general territory in the solar system. Now, on the opposite end, Jupiter and Saturn are very, very, very far out. Those are called the gas planets. We don't even know for sure. In fact, we pretty much assume that they don't even have any hard surface at all. They are absolutely enormous. Jupiter alone has the mass which equals 2.5 times the sum of all the masses of all the other planets. Jupiter rules the solar system and can really raise havoc on it, but we won't get into that. It doesn't really have anything to do with climate change. We're going to mainly be focusing on Mercury, Venus, Earth, and Mars, because I don't think Jupiter and Saturn has anything to do with it. Uranus and Neptune are between they're sort of in between the gas giants and the rocky planets. We're now going to take a look at the surface areas of our nearby neighbors. And keep in mind that scientists believe at one time the surface of these planets was exactly equal to the surface area of Earth. And you'll see how different they are today. So this diagram, this picture of Mars, you can see there's no signs of any life. There's no vegetation. There's no water. It's just a dried up hunk of rock. Here's a larger picture of Mars. Third picture of Mars. Mercury, the same thing. No water, no signs of life, just a dried up hunk of rock. Venus, the same thing. The Venus pictures are usually have an orangish tint to them, and that is because of their very dense atmosphere that they have. The hard part of the planets are very identical. The atmospheric contents vary tremendously. Another picture of Venus. All this in comparison to Earth, which is flourishing with life, many, many species, filled with water on the surface, much, much different than our neighbors. But again, it's actually, it believes, the scientists believe that all the planets were like Earth at one time, and what's happened is the sun has killed 3, and it's 3 down and 1 to go. Now, humans are, I don't know what the value of this is. It might not be, we're not going to spend much time on this. I'm showing you the maximum official recorded winds on some planets, because humans are being blamed for causing increase in storm activity, and I don't doubt for a minute that that is true. However, it's important to see what's going on the other planets to put things into perspective. So these are the maximum official recorded. The Earth, 231 miles per hour. Mars, 70 miles per hour. Venus, 250 miles per hour. Mercury, no wind to speak of. Mercury has almost no atmosphere. It's just a great big hunk of rock, and that's it. And you can't have winds if you don't have an atmosphere, because you don't have any molecules to blow around. Now, just for the heck of it, we're going to take a look at the bigger planets. Jupiter, 900 miles per hour. Saturn, 1,600 miles per hour. Neptune, 1,500 miles per hour. And if these speeds aren't high enough for you, the highest wind speeds ever recorded by NASA is some planet way out, 64.5 light years away, way out into the deep universe, 5,400 miles per hour. I don't know about you, but I would rather not be in a storm with 231 miles per hour, and I certainly couldn't imagine being in a storm with 5,400 miles per hour. Now let's take a look at maximum and minimum temperatures. Again, we are blamed on raising the temperature, and I don't doubt that that has some truth to it. But the Earth, the lowest temperature ever recorded is minus 126 degrees Fahrenheit. Most likely that was in Antarctica. That's the coldest part of our planet. And then the highest is 136 degrees Fahrenheit, and that most likely was right a neighbor of ours, Death Valley. That's usually the hottest part of the planet. Mars, minus 220 degrees Fahrenheit, plus 70. You can read that right on the screen for yourself. So we can see our hottest temperature is 136, but yet 2 of our 3 neighbors, they are significantly hotter. Now, again, this really doesn't mean anything, because your atmosphere, the atmospheres are different. And of course, Venus and Mercury are closer to the sun. Mars is further away. But one thing I want to point out to you that I think is kind of interesting. Look at the differences between the low and the high temperature. With Earth, the difference is roughly 250 degrees. Mercury is over 1,000 degree differences, et cetera, et cetera. And Venus, as hot as it is, 820 to 900, the difference is only 70 degrees. And this shows you something very important about atmospheres. Atmospheres perform a very critical role in the planet's overall health. What atmospheres basically do from a nature standpoint is they equalize the temperature. They move air around, and the movement of the air basically, there I go, pushing buttons again. Okay, sorry about that. But it plays a very important role, because it takes the heat from the hot portions of the planet and distributes it, moves it over to the colder part. Now, Venus has a very, very small difference because they have a very thick atmosphere. And Mercury has no atmosphere at all. And so you go from minus 290 up to 805. My guess is that literally occurs almost instantaneously. In other words, as the planet is turning around on its axis, forming day and night, as soon as that area gets into shade from being in the sun, it almost instantaneously drops from 805 to minus 290, because there is no atmosphere to prevent. But what it does, the atmosphere slows down the cooling process, so it doesn't cool down so much. So it equalizes out the temperature. All right, enough on this. Massive storms on Jupiter. We like to complain about storms, but if you ever see any video of what they pick up on Jupiter, it's amazing. You can see the large kind of oval down in the lower right section there, right near where this screen is split for some reason. Storms on Jupiter traverse thousands of miles across the would-be surface of Jupiter, and the winds are absolutely phenomenal. Lightning bolts are much stronger than anything we could ever imagine. It's kind of interesting to see some video of storms on Jupiter. Here's a blow up a closer thing of a storm on Jupiter. Neptune, the same thing. This is special photography with the white areas, very, very strong storms on Neptune. Okay, at this point, we are done with the astronomy. And again, just to recap the points, the sun is getting hotter and bigger, and it's ever increasing energy. It already provides way more energy than we need, and that energy is increasing. And it's believed by scientists that it has already killed, the sun has already killed our nearby neighbors, and it's 3 down, 1 to go. We're next. Now, at this point, we're going to change gears, and we're going to take a look at what 4.6 billion years of history of the Earth has to offer in terms of possibilities of what we might expect regarding climate. Now, notice this is 4.6 billion years. And we saw before that the sun is basically believed to be 4.5 billion years. And that is correct according to the general consensus among scientists, that the planets came before the sun. And there's a number of interesting theories about why that happened, of which none of them seem to be particularly of interest to me. I don't think they really know. They're still doing a lot of research and trying to figure out the originations of the universe way back in the past. But anyway, some things are very, very interesting and very, very important even to what happens today. We're going to begin by taking a look at what happened 4.6 billion years ago when the planets were first developed. It is believed that before the planets, all we had in our solar system area what is called solar nebula, or a nickname solar junk. Just a lot of rocks floating around and debris, hunks of metal, et cetera, et cetera. All masses tend to gravitate together. And so what happens is all these floating rocks and everything else, they tend to gather together in clusters. And as the clusters grow in size, the gravitational attraction grows in size. So pretty soon these spheres, these are the starting points of the planet, start growing in size. And as they get bigger, they attract more and more of this debris. And this debris starts flying in. In fact, you could consider this diagram to be like thousands and thousands of meteors coming in and striking the Earth. And we have meteors. We see this a little bit today, but most of the stuff has already been cleared out of the solar system because it's all been attracted by the planets. But what happens is, this is a very high energy, high intensive process, which by the way went on for about 20 million years, the formation of the planets. But as these rocks slam in, they suddenly stop when they hit the mass, and there's a huge transfer of energy from energy due to motion to energy due to heat. And this is very important. You see, that is molten hot, and it was that way for 20 million years. Now, something interesting is happening at this point, which is very important. The metals, which are heavier elements, tend to gravitate towards the center. And it's those heavy metals that gravitate towards the center in this liquid type of environment. And those are the magnets of the planets today, the north magnetic pole and the south magnetic pole. And they play an incredibly important purpose for our existence, because the magnets produce a very large magnetic field that completely surrounds the Earth in the upper atmosphere. And that magnetic field is our primary protection against dangerous sun radiation. Most of that radiation just gets reflected right back into outer space. Anyway, enough on this. This is the formation of the planets. By the way, the heat in the center of the Earth is remnant from this. It's the residual heat from this activity. And in the center of the Earth, it's still believed to be molten. It's liquid, magnets, metal, and that protects us. Now, around 1 million years ago, Mars, which was a smaller planet than we have, they lost their magnetic field. And it's believed the reason why they lost their magnetic field was because this residual heat on Mars in the center cooled off, and the magnets solidified, and they lost their magnetic field. And so the heat in the center of the Earth, which, by the way, gives us all of our volcanic activity, the old faithful geysers in Yellowstone, this all comes from the secondary energy system of the Earth, the center of the Earth, and this has to be independent of the sun, because this 20 million years occurred before the sun was even in existence. Okay, so just a diagram of the Earth today. The inner core is still molten hot, the magnets. The outer core and the mantle are the solid portion of the Earth. The crust is the boundary between the solid portion of the Earth and the gas atmosphere. Okay, just quickly, just going through just some geologic history, very, very fast. 4.4 million years ago, the first oceans were formed. 3.8 million years ago, first life started out believed to be underwater. Animals evolved about 700 million years ago. They look pretty weird compared to the animals that are here today. Plants on the continents about 400 million years ago. Take a look at those pictures. They look pretty weird, with the exception, take a look at ferns in the lower right-hand corner. They appear pretty much the same today as they did 400 million years ago. Okay, we are at the end of the first session. How did I do? Did I get this done
Yes.
in 45 minutes?
Thank you.
Okay. I forgot to ask someone to warn me when I get here, because I have a tendency of going overboard. But
Are there
anyway.
questions? Oops.
How is it that the sun was able to take away all the life and made dead planets out of Mercury, Venus, and Mars, and yet it hasn't done it to the Earth? What was the process that caused that?
I'm not sure if I understand the question. Could you repeat that? By the way, I'm picking up my hearing aids day after tomorrow. My doctor has been telling me for 10 years that I need hearing aids, and I started noticing it this past year, and because I start missing part of the conversation. So sorry about that. I was hoping to have these things before now. Okay.
That's okay. Mercury, Venus, Earth, and Mars are the 4 planets closest to the sun. 3 of those planets are dead. Earth is not. What was the process that made Mercury, Venus, and Mars dead planets?
Well, okay, it was a process just simply because of the heat of the sun in comparison to the atmospheres, because as I say, the ground portion of the planets are believed to be totally identical. The atmospheres are tremendously different, and different types of atmospheres absorb different amounts of sun energy. Now, when the radiation from the sun strikes the upper area of the atmosphere of all these planets, 3 things can start to happen. Some of that energy is reflected right back into outer space. We never even see it. Another component, as the radiation works its way from the top of the atmosphere down to the ground level, some of it is lost. It is absorbed by the atmosphere. And that is seen as a result of increased atmospheric temperature. And that's the culprit of global warming, is we're getting too much absorption into the atmosphere. But now, getting back to your question, what happens is all of the atmospheres are significantly different. And depending upon different gases in the atmosphere have different ratios upon how much energy they transmit right through, let the energy go through, how much they absorb and increases in the atmospheric temperature, and how much are reflected into outer space. So a lot of this, it really becomes quite a complex problem, because you have to look at exactly what gases there are. And I'm not real knowledgeable. I do know Venus has a very large component of both carbon dioxide and also sulfur dioxide. And what happens is carbon dioxide is one of the culprits of global warming, of climate change, because they absorb so much of that energy and convert it into atmospheric temperature. So I really can't give you any specifics on why that has happened. I don't even know as though scientists really know, and I'm not real familiar exactly. I believe, if I recall, that Mars has a lot of carbon dioxide in their atmosphere. I'm not real certain on that, because I didn't sit down and remember exactly what happens. But and Mercury, of course, has no atmosphere at all, so it's just a big hunk of rock absorbing it. But I don't know if anybody really knows specifically why this has happened. They just are firmly convinced that it probably happened just because the planets were so identical in the hard portion, the solid portion. Have I answered that? Have I? Yeah, okay.
Next question.
Okay, all right.
Hi. The magnetic poles I've read have been shifting, and I'm wondering if that's part, in fact, I read that it's happening more rapidly, and if that's part of a natural cycle, or whether it's something new and different, and if so, what might be causing that?
I'm sorry, I need to have you repeat that, please.
Okay, I heard the magnetic poles have been shifting, and I don't know if that's part of a cycle, or it's something new and different, and I've heard it's happening more rapidly, so maybe you could explain that.
Shrinking, did you say?
No, shifting.
Shifting, okay. That could very well be. The north and magnetic poles of the Earth have switched. All of a sudden, the North Pole becomes the South Pole, and the South Pole. It's happened, I think, 4 or 5 times, perhaps more than that. And I think there are some theories about what might happen. I don't know if they really have any full understanding of it. As far as any shift going on right now, I'm not aware of, but it's very possible, because that tends to be cyclic in nature. It tends to repeat itself. And I don't know as though it has any negative consequences. It just basically shifts the direction of the magnetic. We make a chart of the magnetic field as basically coming out of the North Pole and moving up into the atmosphere, and then around, and then back into the South Pole. Now, how real that is, it's a convenient way to chart it out, so it gives us some understanding. But how significant that really is, I don't know. Now, according to that chart, the flow of the magnetic field, if you will change. Right now, from outside of the magnet, it flows from the north to the south. And then inside the magnet, it would flow, it would reverse, it would go from the south to the north. But I'm not aware of that, and I'm not sure where that is or how significant it will be.
Any other questions?
This is probably the basic of the whole presentation. What is the mechanism involved in determining what constitute the atmospheres of our planets, billions of miles away? What is the scientific way they use to determine the wind speeds and also the constitution that makes up these various different atmospheres?
Well, that's a very good question. How do they arrive at this? I don't have any specific answers on it. Astronomy is a very interesting field. It's an interesting science because we only have one tool with which to work with, and that's light. That's it. Now, we can go on the planets, and we can retrieve some of the ground material and bring it back to Earth and look at it. So we can do this. And by the way, we have made multiple visits to every single planet, even Pluto. Although those we really can't land on those gas planets. There's nothing to land on. But it's very interesting because all of our knowledge comes from light. It's only one tool. And exactly how they are able to determine this, I couldn't tell you. There's a lot of big questions. And the amazing thing, another amazing thing is, think about this. We have sent space vehicles to Jupiter, Pluto, and they disappear. They don't come back. They take about 12 years to get there. And it's amazing that we can route these things and get them there. And yet we get all these pictures. And you're talking billions of years of transmission of information. And I do know, and I haven't had a chance to research this, so I'm very, very curious, that communications between these far out space vehicles is a whole special topic, and I can't even remember what it's called. But you know and I know that if you're listening to radio stations as you're driving, it doesn't take long, and you're on a road trip, it doesn't take long before the station you're listening to phases out. And you're only talking about small levels of mileage. We're talking billions of miles, and somehow they're able to focus this in and get the details. It's absolutely amazing. And unfortunately, as I say, that is on my to-do list because I'm always interested in communications, but I really don't know exactly how this works.
Okay, last question.
What will be the primary focus of your January 15 presentation?
Okay, good question. What we're going to do is several things. What we're going to do, we're going to look at how dangerous the Earth has been. And we like to talk about, oh, these storms are so bad and this is so bad. It's nothing like the earlier. We went through 5 major mass extinctions that got rid of almost all life. The formation of life was very precarious because it would come and go. We're going to take a look at that. We're going to take a look at amazing information which is going to show you a total different perspective. If you just look at the temperature change over the last 20, 30, 40 years, we're going to go way back 500 million years, and some of you will be shocked at that findings. Now, who knows what happened 500 million years ago? At best, it's a guess, but it has been a scientific guess, and we're going to show you some amazing things that have happened with the temperature over the 500 million years. And we're going to show you some dramatic, we're going to talk about ice sheets, the melting, and we're going to show you some very interesting things from the past that give you a pretty good prediction, if history repeats itself, which it has, of what exactly to expect from these melting ice sheets. So that's going to be some of the area. And then we're going to look at this. And I'll just tell you this right now, that right now, the entire Earth, all the countries, are focused on the same thing. They're focused on what's called net zero. So we're going to take a look at, we're going to give you a formal definition of net zero, and we're going to show you what oppositions are going on right now that is working against net zero. Net zero may be successful, it may fail. In fact, the way it's defined, it probably will be successful. But there are events that are going outside of the definition of net zero that are tremendously impacting this, which will probably, it has a good possibility of making all of those efforts a failure. We have a very interesting approach to climate change. We are moving so fast. We are implementing governmental policies at huge expenses that have not really been tested. And this is driving some scientists absolutely crazy. There's a lot of politics involved in global warming. We're going to show you the official document, which is the holy grail of climate change. And this is all of this is the document that all governments across the world are forming their government policy. And it's an interesting document. It is probably one of the most misquoted documents that has ever existed, because politicians get their hands on it and they put their twist on it. Journalists get their hands on it, they put their twist on it. And I'm going to show you the source, and it's all available for free. It's all on the internet if you really want to get the scientific information. And that is what is always quoted, but usually misquoted with different. So there's a lot of different interesting things. Now, and I'll just say this much. Right now, we are trying to adapt. And there are people that say the adaptation is going to fail. And we're going to look into some of that. But there is an alternate solution, totally different than how we're addressing climate change right now. And this alternate solution has been around in the scientific community for years. There's nothing new about any of this. And I'll just give you a hint. We're trying to adapt. We're trying to change the atmosphere. We're trying to reduce the temperature. The alternate solution is for people to move. And we'll tell you more about that. We'll tell you where you're going to move to, and it's actually going to occur in 2 steps. So we're going to really dig into this, into being somewhat futuristic. So I hope to see you all on the 15th. I think you'll see some eye-popping situations that come from pretty darn solid scientific research centers. You may disagree with it, and these are guesses, they are educational guesses, but a lot of people have put they put their reasoning behind what they have projected for in the future. So I hope it will be interesting.
Stay tuned. Thank you. Thank you, John. Thank you, everybody, for coming. See you next Wednesday.